You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Chunking refers to the process of splitting documents into smaller, manageable segments before they are embedded and indexed. Because embeddings require fixed-size input sequences, entire books, reports, or long articles cannot be processed as single units. Instead, documents must be divided into chunks that are both small enough to fit within a model's context window and coherent enough to preserve meaning. This segmentation is not merely a pre-processing detail. It determines how information is represented, stored, and retrieved. Each chunk becomes an independent vector in the embedding space, and the way text is split directly shapes the retriever's ability to surface relevant content. In this sense, chunking is one of the most consequential design choices in retrieval-augmented systems. Done well, it ensures accurate and meaningful answers. Done poorly, it can fragment meaning, lose critical context, or generate confusing results for end users. The need for chunking arises because even the most advanced large language models cannot handle arbitrarily long inputs. Models operate within defined context windows, for example, 4,000, 32,000, or even 128,000 tokens in cutting-edge systems, but these capacities are still finite. A corporate knowledge base, a scientific journal archive, or a medical case database far exceeds such limits. Attempting to feed entire documents into a single embedding would be impossible or inefficient. By dividing text into chunks, we create units that fit neatly within context boundaries, allowing them to be embedded individually and retrieved selectively. Chunking thus bridges the gap between the model's limited input size and the real-world scale of information, enabling AI systems to handle corpora that would otherwise overwhelm their architecture. Structural chunking is one of the simplest and most common strategies. It divides documents according to their visible structures: paragraphs, sections, headings, or tables. This method is appealing because it respects existing organization, making chunks intuitive for both humans and machines. For instance, a research paper can be segmented into its abstract, introduction, methodology, results, and discussion. A legal contract can be split by clauses or numbered sections. This preserves the natural flow of the document and reduces the risk of breaking meaning mid-sentence. Structural chunking is especially useful when documents follow standardized formats. However, its effectiveness is limited by the assumption that structure always aligns with semantic boundaries, which is not always true in practice. Semantic chunking takes a different approach by splitting text based on meaning rather than surface structure. Instead of simply cutting at paragraphs or headers, algorithms analyze the content to decide where natural semantic boundaries occur. A semantic chunk might span multiple short paragraphs if they discuss the same idea, or it might break a single long paragraph into two if distinct ideas appear within it. This approach often produces more coherent retrieval units because each chunk represents a self-contained idea rather than an arbitrary slice. Semantic chunking is particularly valuable in domains like customer support or technical documentation, where queries may demand precise, context-rich answers. By aligning chunks with meaning, retrieval results are more likely to provide complete and coherent responses. Overlap in chunking addresses a subtle but important challenge. Information often straddles boundaries. If a query relates to text that falls at the end of one chunk and the start of the next, a strict segmentation may prevent retrieval of the full context. Overlapping chunks solve this by allowing some portion of text to appear in multiple segments, ensuring continuity. For example, chunks might overlap by a few sentences or lines so that no important information is lost in boundary effects. This approach is similar to overlapping windows in audio or video processing, which preserve smoothness across frames. While overlap increases the number of embeddings and storage requirements, it significantly improves retrieval quality, especially for nuanced or context-sensitive queries. Chunk size involves critical trade-offs. Small chunks provide high retrieval precision. Each embedding captures a narrow, specific piece of meaning, making it easier to match queries exactly. However, small chunks risk losing broader context, leading to answers that are technically correct but incomplete or disjointed. Larger chunks, by contrast, preserve context but dilute precision, since embeddings represent multiple ideas and may match queries only loosely. Striking the right balance requires careful experimentation and often depends on the application. A legal retrieval system might favor larger chunks to preserve clause-level reasoning, while a FAQ system might prefer smaller chunks for pinpoint answers. Chunk size is thus one of the most influential variables in embedding pipelines, directly shaping system performance. The impact of chunking on retrieval accuracy cannot be overstated. Because embeddings are generated at the chunk level, the retriever can only return what has been embedded. If a concept is split awkwardly, retrieval may fail to surface the relevant information, even if it exists in the source. Conversely, if chunks are well formed, retrieval can surface coherent, self-contained pieces that directly answer user questions. This makes chunking not just a pre-processing step, but a determinant of whether a retrieval system succeeds or fails in practice. Engineers often find that adjusting chunking strategies yields greater improvements than tweaking indexing algorithms, underscoring its importance in the retrieval pipeline. Structural failures illustrate the pitfalls of careless chunking. Splitting mid-sentence can create embeddings that lack coherence, leading to incomplete or nonsensical retrievals. Breaking tables into separate rows without preserving headers can strip context, producing meaningless results when queries seek relationships across rows. Cutting legal clauses in half may lose the logical flow needed to interpret obligations or rights. These failures highlight that structure alone cannot guarantee quality, and that chunking must be sensitive to the integrity of meaning. Poor structural chunking can lead to answers that are factually correct within a fragment but misleading or incomplete overall. Semantic chunking demonstrates its strength through examples where coherence matters. Consider a user asking about troubleshooting steps for a software error. If documentation is semantically chunked, retrieval surfaces a full block of instructions, including prerequisites and caveats, rather than a stray paragraph that omits key details. Similarly, in customer support, semantic chunking ensures that answers are drawn from self-contained discussions rather than arbitrary snippets. The result is more accurate, helpful, and user-friendly responses. By aligning chunks with natural boundaries of meaning, semantic chunking improves the quality of retrieval in ways that directly affect user satisfaction. Chunking also affects embedding efficiency, since each chunk requires a separate embedding vector. Smaller chunks multiply the number of embeddings, inflating both storage and computational costs. For large corpora, the difference can be dramatic. Splitting into 200 token chunks may yield millions more vectors than using 1,000 token chunks. This creates pressure on storage infrastructure and increases the time required to build and update indexes. Efficiency concerns must therefore be weighed against accuracy, making chunk size and method not only a performance decision, but also a cost decision. Indexing performance is likewise shaped by chunking. Larger numbers of small chunks expand index size, increasing search complexity and latency, while approximate nearest neighbor algorithms mitigate some of this cost. Bloated indexes still slow retrieval and increase memory usage. Conversely, larger chunks produce leaner indexes but may reduce retrieval accuracy. This tension illustrates how chunking sits at the nexus of embedding, indexing, and retrieval, influencing every stage of the pipeline. Effective system design requires considering not just retrieval accuracy, but also the operational costs of maintaining indexes at scale. Evaluating chunking quality involves measuring how effectively retrieved chunks answer real user questions. Intrinsic measures such as overlap with gold standard answers provide one view, while extrinsic evaluations, such as human ratings of coherence, provide another. Stress tests like the needle in a haystack challenge, where critical information is buried deep in text, can reveal weaknesses in chunking strategies. Evaluation ensures that chunking is not treated as an afterthought but as a measurable, optimizable component of the retrieval system. Without evaluation, poor chunking decisions may persist unnoticed, undermining system performance. Different domains demand different chunking strategies. Legal documents, with their intricate cross-references and clause structures, require larger, logically consistent chunks. Medical texts, where precision is paramount, may require smaller, semantically coherent segments to ensure accurate retrieval of symptoms or treatments. Technical manuals may mix both approaches, using structural cues for headings but semantic cues for troubleshooting steps. Recognizing these cross-domain needs ensures that chunking strategies are tailored rather than one-size-fits-all, improving relevance and reliability across specialized applications. Automation of chunking has become increasingly sophisticated. Early approaches relied on simple sentence boundaries or fixed token lengths. Modern algorithms analyze semantics, coherence, and structure to produce smarter segmentations. Some systems use machine learning to detect topic shifts, splitting text when a new idea begins. Others use hybrid approaches that combine structural signals, such as headers, with semantic analysis. Automation is critical at enterprise scale, where manually chunking thousands of documents is impossible. Effective algorithms allow systems to maintain high-quality chunking dynamically, adapting as new data is ingested. Ultimately, chunking choices shape the effectiveness of hybrid search, which combines lexical methods like BM25 with dense retrieval using embeddings. If chunking is poor, lexical search may retrieve fragments with missing context, while dense retrieval may surface irrelevant slices. If chunking is well designed, the two methods complement one another, with lexical search grounding queries and keywords, and dense retrieval capturing semantic nuance. This interplay shows that chunking is not isolated, but integrated with broader retrieval strategies. Good chunking amplifies the strengths of hybrid search, while bad chunking undermines both. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Hierarchical chunking is one of the more advanced strategies developed to balance precision and context in retrieval systems. Instead of relying on one fixed chunk size, hierarchical methods create multiple levels of segmentation. A document might first be split into large sections, such as chapters or topic headings, and then further divided into smaller subchunks like paragraphs or semantically coherent sentences. This enables retrieval at different levels of granularity. When a query demands fine detail, the smaller chunks provide precision. When broader context is needed, the larger chunks preserve coherence. Think of it like zooming in and out on a map. The street-level view shows fine detail, while the regional view provides overarching structure. Hierarchical chunking allows retrieval pipelines to choose the right level for the task at hand, improving accuracy and flexibility. It also reduces redundancy, since overlapping context can be captured through the hierarchy instead of duplicating embeddings unnecessarily. Sliding window approaches address continuity by segmenting documents into overlapping windows of fixed size. Each window overlaps with the previous by a set number of tokens, ensuring that ideas spanning boundaries are preserved. This is particularly valuable for sequential data such as transcripts, code, or narrative text, where meaning often depends on continuity across sentences or lines. The overlapping design means that even if a query relates to content bridging two windows, at least one embedding will capture the relationship. The approach resembles how video is processed in overlapping frames to ensure smooth playback, even when individual frames are cut. While sliding windows increase the number of embeddings, they prevent the brittleness that comes from hard boundaries. They are therefore popular in pipelines where continuity is essential, and where the risk of losing critical cross-boundary information outweighs the extra cost of redundancy. Task-specific chunking recognizes that no single segmentation method works equally well for all applications. Summarization tasks may benefit from larger chunks that capture the flow of entire sections, while question answering requires smaller, precise chunks to pinpoint relevant details. Classification might work best with intermediate chunks that balance detail with breadth. Tailoring chunking strategies to the intended task ensures that embeddings represent the right level of information. For example, in customer support, chunks designed around full troubleshooting steps provide coherent responses, whereas splitting them into smaller sentences would confuse retrieval. Similarly, in sentiment classification, sentence-level chunks may suffice, while summarizing legal arguments might demand entire paragraphs. Task-specific chunking is thus a deliberate choice that aligns retrieval design with application goals, ensuring that results are both relevant and useful in practice. Chunking in multimodal systems extends these principles beyond text. Images, audio, and video must also be segmented into manageable units for embedding and retrieval. In video, chunking might involve breaking the content into scenes or time windows, each represented by a vector. In audio, segmentation often involves splitting recordings by pauses or phrases. In images, segmentation could focus on regions of interest, such as faces or objects, rather than treating the entire image as a single unit. Multimodal chunking ensures that the embeddings represent coherent, interpretable pieces of content, rather than arbitrary slices. This makes retrieval more effective across modalities. For instance, a search for red car in traffic will succeed only if video or image chunking isolates frames containing those elements. Without proper chunking, embeddings lose meaning and retrieval accuracy suffers, no matter how advanced the indexing system may be. Latency considerations reveal another dimension of chunking strategy. Smaller chunks generally make retrieval faster because fewer tokens must be processed during embedding and because each chunk represents a simpler unit to match. However, this speed comes at the cost of requiring more chunks overall, which increases query aggregation overhead. For example, a system retrieving answers from hundreds of tiny chunks must reassemble fragments into a coherent response, adding latency at the aggregation step. Conversely, larger chunks reduce the number of embeddings and indexes but make each retrieval operation heavier, since larger vectors require more comparison. Designing chunk sizes involves balancing these two factors, per query speed and post-retrieval assembly. Poorly balanced chunking can produce either sluggish response times or fragmented, hard-to-assemble answers. The trade-offs must be carefully weighed against the performance requirements of the application, especially in real-time contexts. Evaluation benchmarks, such as the needle-in-a-haystack test, provide stress scenarios for chunking strategies. In this task, a single critical piece of information is buried within a long document, and the retrieval system must surface it accurately. Poor chunking strategies may bury the key detail within large, diluted chunks, making it harder to match precisely. Alternatively, very small chunks might isolate the detail but lose surrounding context, producing answers that are technically correct but unhelpful, without additional background. Benchmarks like this expose the strengths and weaknesses of different chunking methods, offering concrete evidence for choosing one approach over another. They also reveal how chunking interacts with downstream tasks. An effective chunking strategy may excel in precision but underperform in summarization, or vice versa. Benchmarks ensure that chunking is validated in practice, not just assumed as a pre-processing detail. Data freshness complicates chunking strategies in dynamic environments. When content is updated frequently, as in news feeds, code repositories, or product catalogs, embeddings must be regenerated and indexes must be rebuilt. Chunking choices directly affect how costly and time-consuming these updates are. Smaller chunks mean more embeddings must be updated for each change, while larger chunks reduce the number of updates but risk missing localized changes. For example, if a single line in a technical manual changes, updating a large chunk embedding wastes resources by reprocessing surrounding unchanged text. Conversely, if chunking is too fine-grained, constant updates overwhelm the pipeline. Freshness, therefore, becomes an operational challenge tied closely to chunking strategy, requiring trade-offs between responsiveness to updates and efficiency of maintenance. User experience implications highlight why chunking design cannot be treated purely as a technical detail. Poor chunking often manifests directly in the answers users receive. A fragmented response pieced together from multiple small chunks may feel disjointed or incoherent, undermining trust in the system. Large chunks may return verbose passages filled with irrelevant information, frustrating users who want concise answers. Even subtle misalignments can lead to confusing results, such as when a query retrieves part of a table row without the corresponding headers. The ultimate measure of chunking quality is not just retrieval accuracy, but how well answers meet user expectations for coherence, clarity, and completeness. This underscores that chunking is a design decision with user-facing consequences, not merely a pre-processing optimization hidden in the pipeline. Semantic cohesion is one of the strongest arguments for meaning-based chunking. When chunks align with semantic boundaries, retrieval returns passages that are coherent on their own, reducing the burden on downstream systems to stitch fragments together. This leads to outputs that are more natural and human-readable. Consider a user asking about causes of engine overheating. With semantic chunking, the retrieved passage might present the entire set of causes with explanations, making the model's job of generating an answer much easier. Structural or arbitrary chunking, by contrast, might return only part of the list, forcing the system to guess or produce incomplete responses. Semantic cohesion reduces these risks and improves reliability, ensuring that chunks themselves embody meaningful units of knowledge. Hybrid chunking approaches combine structural cues with semantic analysis to capture the best of both worlds. Documents are first segmented according to structure, such as section headings or paragraphs, and then refined by semantic methods to split or merge chunks where appropriate. This ensures that formal boundaries are respected while also accounting for meaning. Hybrid strategies are particularly valuable in domains with complex formatting, such as technical manuals or legal documents, where structure alone cannot guarantee semantic coherence. By layering structural and semantic signals, hybrid chunking creates embeddings that are both efficient to index and reliable in retrieval. It represents a pragmatic compromise between rigid structure and flexible meaning, making it one of the most widely adopted approaches in real-world systems. Scalability challenges emerge when enterprises attempt to apply chunking strategies at massive scale. A multinational corporation may need to process millions of documents across languages, formats, and domains. Manual chunking or ad hoc strategies quickly become infeasible. Automated systems must handle this scale efficiently, but automation introduces its own risks, such as misinterpreting formatting or failing to recognize domain-specific boundaries. Enterprises must therefore invest in robust pipelines that combine automation with domain expertise, ensuring quality even at scale. Scalability also increases the importance of consistency. If chunking strategies vary unpredictably, embeddings become less reliable, retrieval becomes inconsistent, and downstream applications suffer. At global scale, chunking is not just about performance but also about governance and standardization. Research on adaptive chunking seeks to make segmentation dynamic, adjusting chunk size and boundaries based on query type or task requirements. Instead of embedding all documents into fixed-size chunks in advance, adaptive methods segment documents differently depending on the use case. A summarization query might trigger larger chunks, while a factoid query might generate smaller ones. Adaptive chunking can also exploit model predictions, adjusting segmentation based on likelihood of relevance. While still experimental, these methods promise greater flexibility and efficiency, as they avoid the one-size-fits-all limitations of static chunking. If successful, adaptive chunking could represent a step towards systems that manage chunking intelligently, optimizing retrieval pipelines in real time based on task demands. Cost considerations cannot be ignored in chunking design. Smaller chunks increase the number of embeddings, inflating storage costs and retrieval index sizes. They also increase inference costs, as more chunks must be processed per query. Larger chunks reduce these costs, but may reduce retrieval precision, leading to downstream inefficiencies as irrelevant content is retrieved. For organizations operating at enterprise scale, these costs accumulate into millions of dollars annually. Chunking is therefore as much an economic decision as a technical one. Balancing retrieval accuracy against storage and compute costs requires careful modeling of trade-offs, particularly for industries with thin margins or massive data volumes. Security and compliance introduce further requirements for chunking strategies. Sensitive documents may contain personal or confidential information that must not be exposed. Chunking strategies must ensure that sensitive fragments are either redacted or isolated, preventing retrieval systems from exposing them inadvertently. For example, in healthcare, chunks may need to exclude identifiable patient information while still embedding the relevant medical content. Compliance with regulations such as GDPR or HIPAA adds layers of complexity, requiring organizations to treat chunking not only as a performance optimization but also as a legal and ethical responsibility. In these contexts, chunking pipelines must be auditable, ensuring that sensitive data is handled correctly at every stage. Finally, chunking strategies connect directly to re-ranking systems, which refine results after initial retrieval. Even with well-designed chunking, retrieval may surface multiple candidates, some more relevant than others. Re-rankers reorder these candidates based on contextual relevance or user intent, ensuring that the final output is as accurate and coherent as possible. Chunking determines the raw material available for re-ranking. If chunks are poorly formed, re-rankers must work harder to assemble coherent answers, and some information may be irretrievably lost. Chunking and re-ranking thus work hand in hand, forming complementary stages in the retrieval pipeline. The bridge between them illustrates how segmentation choices ripple through the entire system, influencing everything from embedding quality to final user experience. In conclusion, chunking strategies determine how documents are split, embedded, and retrieved, directly shaping the accuracy, coherence, and cost of AI pipelines. Structural chunking offers simplicity, semantic chunking offers coherence, and hybrid approaches balance the two. Hierarchical and adaptive methods promise flexibility, while domain-specific needs demand customization. Poor chunking leads to fragmented, confusing answers, while strong strategies yield coherent, context-rich responses. Because chunking influences everything from storage costs to compliance, it must be treated as a central design decision rather than a pre-processing afterthought. As retrieval-augmented generation continues to expand, chunking will remain one of the most critical levers for improving both system performance and user experience. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.